Thank you very much for introducing. So we'll be speaking about covering Hypercube with hyperplanes. So the first question we could ask is, how many hyperplanes are needed to cover a hypercube? So if we ask it this way, the answer is very simple because we just need two hyperplanes. For instance, the first coordinate is equal to 0 and the first coordinate is equal to 1. So once we're done with this question, we can try something else. For instance, now we want to cover everything up to one point. So we don't want to cover the point 0, but we want to cover everything else. So at this moment, we cannot use just those two hyperplanes as above because we would cover everything. But if we think a bit, then we will realize that if we use n hyperplanes of the form ith coordinate equal to 1, then we will cover everything as we want it. But this is not the only option, because we can also consider another hyperplanes. Namely, we can ask what is the sum of the coordinates, and we can iterate over all possible sums from 1 to n. In this way, we will also cover every point which is not the point with all zeros, and also we will use n hyperplanes. So the question is whether it is the best possible solution. And this is the answer from Alon and Freddy from '93, that exactly we need at least n hyperplanes to cover a hypercube. And the proof uses something from algebra, which is called combinatorial Null-Stellensatz. It is a combinatorial version of Hilbert's Null-Stellensatz theorem. And it was introduced by Alon and Freddy as a very useful tool for proving various stuff from number theory and combinatorics and also other fields of mathematics. So maybe let me state it, this combinatorial Null-Stellensatz. So we have a polynomial, I denoted it by p, in n variables over some field f. It can be a finite field or infinite field. So it is just some arbitrary field. And we suppose that the degree is equal to something. And this is sum of some non-zero integers. And we suppose that the coefficient of xi to the power of ti, this product, is non-zero. So in this case, if we consider some subsets of our field f of sizes bigger than ti, then we will find a point in this product of those subsets, which is not a zero of this polynomial. So in our case, we would like to, so if we want to use combinatorial Null-Stellensatz to prove Alon-Freddy theorem, then we will consider hyperplanes, and each hyperplane is given by some linear equation. So in particular, we will be interested in polynomial which is of degree n and which is linear with respect to f. Actually, Alon and Freddy proved something more general. Namely, they considered a collection of finite subsets over arbitrary field f, and they proved that if we want to cover all points of this product but one, then we need to use at least that many hyperplanes. I mean, this is the sum of the sizes minus n, actually, we can say. Okay, so that's about it. So let's ask another question. I mean, how many hyperplanes are needed to cover each point of our hypercube, at least k times? And again, we don't want to cover the origin of our space, so the point 0. Of course, we can use our previous cover and apply it k times, but this is a very inefficient way of covering our hypercube. And actually, we can use just slightly more than n hyperplanes. And why is that? Because if a point from our hypercube has more than k non-zero coordinates, then it is actually covered k times by using our hyperplanes of the form xi equal to 1. So the only points which are not covered k times are those points which have only a few number of non-zero coordinates. And we can cover them by using another hyperplanes of the form the sum of coordinates is equal to something smaller than k. And of course, we can use the same hyperplane multiple number of times. I don't restrict those hyperplanes to be different. So we actually consider something like multi-set of hyperplanes. On the other hand, we know that n plus k minus 1 hyperplanes are really necessary. And it is a very simple argument, because if we remove k minus 1 hyperplanes from our cover, then each point would be covered at least once. And this is just Alan-Furedi theorem, which claims that, okay, so in this case we need at least n hyperplanes. We can also write the minimum number of hyperplanes needed as f, n, and k. And we will use it to state the result of Clifton and Huang from 2020, who proved that for every n at least 2, if we want to cover each point which is not an origin at least thrice, then we need to use n plus 3 hyperplanes. And this is the exact number. And if we consider a bigger multiplicity, like at least 4, and consider at least 3 dimensions, then we have a slightly better bound than the one which is trivial from Alan-Furedi. So instead of n plus k minus 1, we have n plus k plus 1. Also, they considered a case when n is fixed and k goes to infinity, and then the number of hyperplanes which we need to use is equal roughly to k times the harmonic sum from 1 to 1 over n. Okay. But we have also a slight improvement of the lower bound, and it is due to Sauermann and Widgerson from the same year. And they proved some algebraic result about polynomials. And as we will realize, it is really something which we need to get some lower bound. So what do we have? So we have some k at least 2, it is our multiplicity. And we have some n which is bigger than something, for instance 2k minus 3 for the theorem to work. So we have some polynomial of multiplicity at least k at all points which are not the origin. And also we assume that 0 is not a big multiplicity. So it is not a zero multiplicity of at least, for instance, k times k minus 1. And then we claim that the degree of p must be at least n minus 2k plus 3. So if we take the equations of our hyperplanes and we multiply them in order to create a polynomial, then if those hyperplanes covered each point of our hypercube at least k times, then we get immediately the result that we had to use at least n minus 2k plus 3 hyperplanes. But they proved something more, namely that for each L, which is from 0 to k minus 2, there exists actually a polynomial which has exactly this degree, n plus 2k minus 3, which has all multiplicities at least k at all points which we need. Of course, it is in without origin. So yeah, here it is without origin, and such that p has a 0 of multiplicity exactly L at the origin. So of course we have some corollary which I already stated, but there is also another corollary, namely that this polynomial method may be not very effective to get the correct bound. like when I go back to here. So we know that we need at most n plus k choose 2 hyperplanes, and we need at least n plus k minus 1 hyperplanes. And the question is, which number is more exact? And Clifton and Huang, they conjecture that actually we need n plus k choose 2. And for a very simple reason, namely they just couldn't find any better hyperplane cover of our hypercube. So if they are correct with this bound, then we actually need some better tool than just polynomial method. Okay, so let's move on to yet another question, but in a bit different direction. Namely, we now want to cover each point of hypercube with some restricted set of points. And we ask again how many hyperplanes are needed to cover such a subset. So actually, we have already one result of this kind. It is by Alon and Faraday from '93. And it says that if we use m hyperplanes to cover some proper subsets of our hypercube, and we use a number of hyperplanes strictly less than n, okay, or not greater than n, then we miss at least 2 to the power n minus m points of our hypercube. And actually, this is a corollary from Alon and Faraday theorem. And why is it so? So we can prove this corollary by induction on the difference n minus m. So if this difference is equal to zero, then it is obvious what we need to prove. If this difference is equal to 1, then it follows from Alon-Faraday theorem. So let me state the inductive step. So we use some number of hyperplanes, and we know that there are at least 2 points which are not covered. I mean, I denoted this set of points which are not covered by S. And those 2 points are different, so they differ at some coordinate, which I denoted by I. So if I consider now 2 smaller hypercubes, one hypercube defined by the equation that the ith coordinate is equal to 0, and the second hypercube defined by the equation that the ith coordinate is equal to 1. And if I restrict our hyperplanes to those hypercubes by saying that the ith coordinate is equal to either to 0 or to 1, then both of those hypercubes are not covered by our hyperplanes. And we can now apply our induction hypothesis because the difference is now smaller. It is n minus 1 minus n. So each of those hypercubes each of those has at least 2 to the power n minus 1 minus m points which are not covered. So if we multiply this number by 2, we get that in our original hypercube we had at least 2 to the power n minus m uncovered points. Okay, so let me introduce some notation. So for a subset of our hypercube, we define the exact cover number of B. We will denote it as EC of B, exact cover, as the minimum number of hyperplanes which we need to cover exactly B. So by Alon-Faraday theorem, if we consider a set B of the form whole hypercube minus 1 point, then we know that this exact cover number is just equal to n. Here comes our first result. So we actually studied what happens if we make the set S slightly larger. So for instance, if we remove 2 or 3 points, then we need exactly n minus 1 hyperplanes to cover such a set. And if we remove 4 points from our hypercube, then we have 2 possible options. One possible option is if there exists some hyperplane which covers exactly 3 points from our restricted set S. In this case, we claim that the exact cover is equal exactly to n-1. Otherwise, if it's not the case, so all 4 points are in the same hyperplane, then the exact cover number is equal to n-2. Okay. So how do we prove such a result? So to get the lower bound, we just use the corollary by Allen and Furedi, and we know that n-2 hyperplanes must miss at least 4 points, and in the same way, n-3 hyperplanes must miss at least 8 points. So we get some lower bounds. For instance, we get a correct lower bound for a problem when the size of S is at most 3. And we get the lower bound n-2 if the size of S is equal to 4. To get the correct lower bound for the second case, like when there exists some hyperplane Q which covers exactly 3 points from our S, then just note that if we add this hyperplane Q to our hyperplane cover of our set Hypercube minus S, then we will get a cover of all points of our hypercube but 1. So actually, we had to have at least n-1 hyperplanes at the very beginning. So this is how the lower bound works. But we still need to get the upper bound, so we actually need to prove that we actually can cover such subsets using such number of hyperplanes. So for instance, if we remove 2 points, so how does it look like? So we can assume that one of those points is just the origin because hypercube is symmetrical. The second point is some vector u, which we can write by some permutation of coordinates in the form that the non-zero coordinates are just the first L coordinates. And in this case, we can just use n-1 hyperplanes of the following form. So some of them are just that the ith coordinate is equal to 1. So it is for those coordinates where ui is equal to 0. So, and also we need to deal with the case with the remaining points. And we just realize that the sum of first L coordinates is always equal to 0 or L. So we add hyperplanes of the form that the sum of first L coordinates is equal to something between 0 and L. So from 1 to L-1. And it is, I believe, easy to see that such hyperplanes indeed cover everything what we need. So if we want to find upper bound for the size of S equal to 3, then we proceed in a similar fashion. So we first assume that we have some vectors, which we don't want to cover. So it is some origin, it is some vector v and w. And also we can permute the coordinates in such a way that the set of non-zero coordinates for the first vector is just the set of first a plus b coordinates. And for the second vector, the non-zero coordinates are first a, and c coordinates from a plus b plus 1 to a plus b plus c. Also, we can assume that actually c is positive. It is just an assumption. Okay, and how do we proceed? So the first one we can consider is just taking hyperplanes of the form the ith coordinate is equal to 1 for indices bigger than a plus b plus c. So in this way, we'll use n minus a plus b plus c hyperplanes. And we need to find some more. So note that for each point from our restricted set, we have the following properties, that if we take the sum of first a coordinates, then it is either 0 or a. If we take the sum of the next b coordinates, then it is equal to either 0 or b. And if we take the sum of the next c coordinates, then it is equal either to 0 or c. So we can consider hyperplanes of the form that the sum of appropriate coordinates is equal to something in between. So like between, for instance, 0 and a in case of first a coordinates. Okay, that would be still not enough because we'll still have some points which will be not covered. And every such point will satisfy first the equations which we denoted by star. And second, they will also satisfy the equations of the form that the ith coordinate is 0 for indices bigger than a plus b plus c. And now we need, unfortunately, to consider some cases, but actually there are only two. The one case is if both a and b are bigger than 0. In this case, we used n-3 hyperplanes, and we need to use 2 more. And otherwise, exactly one of a or b is bigger than 0, and the second one is just 0. And then we used n-2 hyperplanes, and we just want to find one more. Let's not analyze it thoroughly, but if we consider the first case and we need to find 2 hyperplanes, then they are of this form. Maybe I'll not go into the details why this works, because we'll see it in a moment, and then it would be more evident why such hyperplanes work. And also we have some hyperplane for the case when a is equal to 0, and some hyperplane when also b is equal to 0. And there is also some conclusion that in each case we actually used n-1 hyperplanes. So let me just say a few words about the case when the size of S is equal to 4. So we proceed in 2 steps. So the first step is to reduce it to the case when the dimension n is not bigger than 7. And there is also a second step when we just want to deal with this case when n is not bigger than 7. So for the first step, we want to use the following lemma. So we assume that for some indices, I smaller than j, we have the equalities for all vectors from our set S. So this assumption we can write in a different way. Namely, we can consider a matrix. In each matrix, we write some points from our set S. So we have first vector, we have second vector, and so on. We have actually 4 vectors in now. So what we claim in lemma 1 is that if we find 2 columns which are identical, so this is I and this is j, then we can actually remove one of them and just go one dimension lower. I mean, to take one step down from n to n-1. So for simplicity, we can assume, if we want to prove it, that actually I is equal to 1 and j is equal to 2. We can assume this because we can just permute the coordinates, and we will essentially don't change anything by this. So we consider that we took some hyperplane cover of our restricted set. And now we want to lift each hyperplane to some hyperplane in n dimensions. And we do it in a very simple fashion. Namely, if we had some equation, I mean the sum alpha k xk equal to b, then we exchange the first summand by the sum x1 plus x2 divided by 2. And the rest is essentially the same. We just need to make a small shift because we actually used two variables. So what we claim is that if we take this L of h and we also add one more hyperplane, which is of the form that the sum of first 2 coordinates is equal to 1, then we will actually get a hyperplane cover of 0, 1 to the power of n, I mean of our hypercube, without our set S. So what we did for the case S equal to 3 was exactly applying this kind of lemma, but we did it a number of times at once. So instead of just removing one column, we wanted to remove L columns, so we would get a very similar equations for our hyperplanes. Anyway, if we apply this lemma one several times, then we can reduce the dimension and we will get some upper bound for the dimension. Just maybe let me say, why is this equal to 7 and not 8? Because if we have what I wanted to say, oh, actually this is a very good question for me at this moment. Okay, because if we have our matrix and we write our 4 vectors in this matrix, then one of those vectors is actually all zeros, because we assumed that one of those 4 points in our set S is the origin. So we actually have only 3 vectors which can have some non-zero entries. So for instance, let me write it in this way. And if it happened that we have some, so in general, we have 8 possibilities for how the column may look like. And one of those possibilities is when all of those coordinates are actually equal to zero. And if this is the case, so it is the ith coordinate, then we can just use the hyperplane of the form the ith coordinate is just equal to 1. And by using such coordinates, we can just assume that we have, we can reduce the dimension, or we can just forget about such columns. So in fact, we have only 7 possible choices for a column. 7 different choices. So that's why we can reduce the dimension to 7 and not, for instance, 8 or 16. Okay, so there is also one important remark, namely that if there existed some hyperplane which covered exactly 3 points from our set S, then after this reduction, we will still have some hyperplane which would cover exactly 3 points in our in the lower dimension. And I think the easiest way to realize it is just to note that by removing the duplicates of columns, we don't decrease the rank of our matrix. So if the points were in general position, then they still stay in general position. Okay, and how to deal with the case when the dimension is small? Unfortunately, we couldn't find any nice approach, so we just used computer search. So we just checked all possible configurations of columns and realized whether we can cover them using an appropriate number of hyperplanes. And this is also a not very nice thing, because we couldn't find any easy tool to deal with the case, for instance, when the size of S is strictly bigger. We could do it by hand still, but it would be very annoying. Anyway, we can still ask whether we have this equality that if we remove some evident column from our set, then actually we get the equality. So if we go to 1 dimension lower, then we can just add the 1 plus 1. So we have some counterexample by Adam Salt-Wagner, who considered some set S in 4 dimensions, 4-dimensional cube. And we can check it by hand that we need at least 3 hyperplanes to cover the set S. But if we consider our extended set S in 6 dimensions, I mean just by adding 2 zeros at the end of each our points from the set S, then actually the number of hyperplanes is needed is lower and is equal to at most 4. Okay, so that was about a very small number of removed points. So let me move to something maybe more exciting, let's say. So now we'll introduce two notions. The first one is about removing a set of size equal to k from our hypercube, and we are looking for the worst case scenario. So the scenario when we need to use the biggest number of hyperplanes. So that's why we consider the maximum. And also we are just looking just for the worst case scenario without the restriction on the number of points removed. So we are just looking for the subset of hypercube which is very hard to cover. So for the first case, if we fix some integer k and we go with n to infinity, then actually it is not very surprising that the number of hyperplanes which we need is roughly just n. And also we have a second result that if we are looking for the most nasty subset of our hypercube, then actually we need a huge amount of hyperplanes, which is roughly exponential if in n, but it is exponential divided by some polynomial. It is either quadratic or linear. So Theorem 2 is actually an observation from the results which I already showed, because to get the lower bound we just use the color by Alon and Furedi. Because if we use a small number of hyperplanes, then we need to miss a large number of points. And for the upper bound, we can use our lemma about removing the columns, which are duplicates, and we can realize that the exact cover of nk is not greater than the exact cover in a very special case when n is equal to 2 to the power of k plus n minus 2 to the power of k. So indeed it is mostly linear. And for the theorem 3, we will need some tools to prove such a result. And to get the lower bound, we will introduce the notion of an intersection pattern. So we say that a subset of a hypercube is an intersection pattern if it is equal to the hypercube intersected with some hyperplane. So our lemma says that a hypercube has at most 2 to the power n squared intersection patterns. So it is quite an improvement if we compare it to the number of all possible subsets, which is 2 to the 2 to the n. And how do we prove such a result? So we will want to assign each pattern to some unique element of the nth power of a hypercube. So this is our goal. And how do we start? We start with taking any point of our pattern. And we consider the operation of coordinate-wise addition modulo 2. And in fact, if we add this point x to every element of P, then we will get just the same set but reflected along some axis determined by x. In particular, this set would contain 0 because x plus O plus x is 0 and it belongs to x O plus P. So how do we proceed? Now we choose any maximal independent subset of this x plus p so that the hyperplane, or just the plane, the hyper subset, maybe not hyper, but the span of those vectors intersected with our hypercube is equal exactly to x plus p. Of course, we may note that this subset is of size at most n-1, because if it was of size n, then we would get, of course, the whole hypercube. And finally, what we do, we just associate this set of vectors to P. And why is this a good association? Because if we have vectors from V1 to Vk, then we can reconstruct how the x plus P looks like. And then by applying one additional addition, I mean x plus P, then we will reconstruct the pattern P. So actually, if you are given such a set of vectors, then you can reconstruct the pattern. Okay, so this proof could look like a bit crude. I mean, it wasn't very sophisticated, maybe let's see, but actually the actual number of intersection patterns is really close to what we just proved. It is just a difference of some small factor at the n square. Okay, so how can we use this to prove that the exact cover of any subset is at least of some subset is at least 2 to the power n-2 divided by n square? So we will use the probabilistic method, and we will choose our set S by random, by including each point independently with the equal probability 1/2. So if we consider some intersection pattern and we ask what is the probability that it is disjoint from our set S, then it is just equal to the 1/2 to the power of the size of P. So if we consider the probability that our set S is disjoint from all the intersection patterns of size at least twice n square, then we can bound this probability by this sum, and this sum we know that has at most 2 n square summands, and each of those summands is not greater than 1/2 to the power of 2n square. And as we can easily see, this is really small o of 1. This is really going fast to 0. Also, the probability that the set S is not too large is equal to 1/2. I mean, it is just half the number of points of our hypercube. So we can conclude that there exists some subset of size exactly 2 to the power f n-1, which has non-empty intersection with every intersection pattern of size at least 2n square. I mean, we know that the size of S is not larger than 2 to the power n-1, but of course we can just add any points to the set S, and we will not destroy this property. So finally, in order to cover our hypercube without set S, we need to use only intersection patterns which are small, I mean of size less than 2n square. So in other words, we need to use at least 2 to the power n-1 divided by 2n square, which is just 2 to the power n-2 divided by n square hyperplanes. Okay, so this is how the lower bound works. So how about the upper bound? So now we want to prove that however the set S looks like, we can cover it using okay, maybe not too large is not a very good word, but using some number of hyperplanes. So for the upper bound, we will need slightly different tool. So we'll start with introducing the Hamming distance, which is the number of coordinates at which two vectors differ. So actually, we can write it as the sum of absolute values. So also we can introduce a Hamming sphere. So this is just the set of points from our hypercube, which are at Hamming distance 1 from some fixed point y. Of course, every such Hamming sphere will consist of exactly n points, because those points which are from Hamming sphere differ from y at exactly one coordinate. Okay, so the main observation is that every subset of our Hamming sphere is an intersection pattern. So in order to observe it, we need to observe it just for the Hamming sphere around the origin, because Hypercube is just symmetrical. And the first thing is to realize that the Hamming sphere itself is an intersection pattern, and it is an intersection pattern because we just consider a hyperplane consisting of all points whose sum of coordinates is equal to 1. And in order to get a subset, we just intersect our Hamming sphere with some hyperplanes of the form that the ith coordinate is equal to 0, and then we find just an extension of this subspace of lower dimension. And we just want to avoid additional points from 0, 1 from our hypercube, but it is of course always possible. And we will need one more result. It is from Cham from 1990. So it claims that there exists a subset of hypercube of size at most 2 to the power n plus 1 divided by n, such that for any point from our hypercube, it is at distance 1 from some point from our subset D. So if we have such a result, then how do we proceed? So first we fix some subset B which we want to cover, and we choose a subset D as above. And now, for each point of the subset D, we know that the Hamming sphere around this point intersected with B is an intersection pattern. And also, because of the property of the subset D, we know that sets of this form cover whole B. And in this way, we can use as many hyperplanes, that many hyperplanes as many are in a subset D. And we know that the subset D is of size at most 2 to the power n plus 1 divided by n. So this is our upper bound for the number of hyperplanes which we need. Okay, so this is what we showed. So we showed that in the worst case scenario, we are between roughly 2 to the power of n divided by n squared and 2 to the power of n divided by n. So actually, Alon proposed some improvement to the lower bound. It is actually very easy improvement, but it is just improvement by a factor of 4. So to the 2 to the power of n divided by n squared. And the question is if we can improve it any further. And I think that's all what I wanted to say today. So I think it was really short, but it just leaves us more time for any questions. So thank you very much for listening.